So in this video we are going to come up with the derivative shortcut for both the sine of x as well as the cosine of x, making use of the limits that you saw in the previous couple of videos. So going back to the definition of the derivative evaluated as a function, this will be the limit as h approaches 0 of the sine of x plus h minus the sine of x all over h. Now, obviously, if we attempt to use the direct substitution property, bad things will happen at this point. We will wind up with 0 divided by 0. So I'm going to use a sum identity. That is the sine of a sum. So this is the sine of x times the cosine of h plus the cosine of x times the sine of h. So again, sum identity for the sine. Now with that in mind, some of these terms have a sine of x and some of them have a cosine of x, and I would like to separate those out because we're going to see those familiar limits show up in here. So if I take everything that has a sine of x and I factor out the sine of x from it, there are two terms that I'd be talking about. This first term that we got from the sum identity and the last term that we got from the definition of a derivative. So when I factor out a sine of x from the first term, I will be left with the cosine of h. When I factor it out of the last term, I'll have a minus 1. This is all still as a fraction divided by h. Now if I do the same thing with all of the term that has cosine of x, well, there's really just this one right here. That will be the sine of h over h. Now, hopefully you recognize these two things as the limits that we derived in the last couple of videos. In this formula, though, we're making use of the variable h rather than the other variable that was used, theta. So this one is going to be equal to 0, and this one is going to be equal to 1. Meaning that once I do that, I am going to wind up with the cosine of x. So, big important conclusion that we can draw from this is that if I were to differentiate the sine of x, I get the cosine of x. Now we will see something similar when it comes to the cosine function, and I'd like to do that down at the bottom part of this page. We'll call this one y, just to switch things up a little bit. So dy dx is going to be equal to the limit as h approaches 0 of the cosine of x plus h minus the cosine of x all over h. The work that I'm going to do here is identical to the work that you saw up at the top part of the page earlier in the video. First we'll apply a sum identity to the cosine. Now the sum identity for the cosine says take the cosine of the first angle times the cosine of the second angle minus the sine of each of the angles. Minus cosine of x all over h. Same thing as what we did up top. I am going to take anything that has a sine of x in it. I'm going to factor that out. The only thing that has a sine of x in it, though, is this term right here. When I factor that out, I will be left with negative sine of h over h plus the cosine of x times. There are two terms that contain a cosine of x, this one right here and this one right here. When I factor out that cosine of x, the first term becomes the cosine of h. Second term becomes minus 1 all over h. And we see the exact same two limits that showed up earlier. Now without the negative sign, limit as h goes to 0 of the sine of h over h is equal to 1. Or more specifically, because of this negative sign that's in here, it'll be negative 1. This, however, is simply going to be 0. Limit as h goes to 0 of the cosine of h minus 1 all over h. Therefore, when we apply those limits, we are going to get sine of x times negative 1. So negative sine of x. So expressed as a derivative shortcut, the derivative with respect to x of the cosine of x is equal to the negative sine of x. Now, I would like to give a short explanation graphically as to why this hopefully makes sense. So I'm going to create a little graph here. X-axis, y-axis, and I would like to consider y equals the sine of x. That was the first function that we differentiated. So sine of x starts at the origin, goes up, comes back down, and goes back to the x-axis, and that's what one full period of the sine function looks like. Now, as far as the derivative of this is concerned, you'll notice that the function starts off increasing, so the derivative is going to be positive. That is until we get to the local maximum where the derivative would be 0. Then it starts decreasing until we get to that point and continues to decrease until we get to about here, and then starts increasing again. So derivative is positive, then 0, then negative, then back up to 0, and then back up to positive. You'll notice that what I just created is exactly a cosine function. Whereas if we were to replicate this process with the derivative of the cosine function, we start at a local maximum, which means that we would have a derivative equal to 0. Then we start decreasing, which means that the derivative should be negative until we get to a local minimum where it should be 0 again. Then we start increasing, so it should be positive until we get to a local maximum where the derivative would be 0. You'll notice that the graph that just got created is the graph of the negative sine of x. And if I had one more color of ink here, I would go ahead and differentiate it one more time, and we would get a negative cosine of x, but that's just the constant multiple rule at that point. So hopefully this helps make it kind of clear as to why these derivatives work the way that they do.